So our today's lesson is on dimension analysis. This is a very important topic that you need to pay total attention because it will help you. It acts as a foundation for many topics. So like as you'll be dealing with physics, this topic comes into effect or into application in a number of topics. So before we understand what dimension analysis is, we need to know what are dimensions. So dimensions are physical nature of quantities. Okay, a physical nature of a quantity, and this nature may be mass, length, or time. So there are many physical nature of quantities, but these three are the main quantities that we are going to talk about. So these quantities are what we call basic quantities, which we are going to use to derive other quantities, which we call derived quantities. I'm sure everyone is clear on that point. Now, dimension analysis, it is now a method that is going to use or which come into effect when we want to check the consistency. We want to check the consistency, derive formulas, and convert units by dimensions. So we need to also know the importance of dimension analysis. So dimension analysis, one, is used to check the correctness of physical quantities. So when we want to know if a physical quantity is correct, we are going to use dimension analysis. This is going to make sense very soon when we start practicing exam questions. The other thing is that dimension analysis is used to derive the relationship between physical quantities. Wow, this is an interesting application of dimension analysis. So in physics, to be true with you, there are a number of equations which you cannot master all of them. Like in each semester, you are going to learn about maybe more than 100. Now, can you manage to master all those equations? That's very difficult. Or if you will try, you will just add a burden upon yourself. Rather, dimension analysis, it will help you to derive equations. Even if you don't know, you meet a question, you can know the right equation to use through dimension analysis. We can also use to convert units from one system to another. There are three systems. We have the SI system, we have the CDS system, we also have the US system. So these are actually the systems I'm talking about. So this system of units can be converted from SI to CDS system using dimension analysis. So let's start. So I earlier talked about mass, length, and time as the three important basic quantities which are going to reign as a foundation of these other quantities. So on this point, we are going to know the dimensions of mass. Take note to this, they are very important. Mass, we know the symbol of mass is m, but my main area of interest is to know its dimension. So wherever you see mass, you know to say that its dimension is m, capital letter M enclosed in square brackets. So is length and time. Now, these three quantities now, the dimension of these three quantities can be used now to derive quantities. These are other quantities which may be distance, velocity, and acceleration. So, distance, as we can see, it has no formula, but its dimension, it's L. Actually, here, I can just say this is length. I mean length. No, my handwriting is not okay. Yeah. So this is range, and the dimension of range is L crossed in square brackets. Now, what are the dimensions of velocity? Yeah, this comes very interesting, whereby velocity we know is distance over time. So, to find the dimensions of velocity, we have to put the dimension of distance as the numerator and the dimension of time as the denominator. That's where we come to have L over T. Now, we know to say that I over T is same as T raised to the power I. So that means L over T is same as L times T to the power I. This is also the dimensions for velocity. Take note of this. They are very important and they'll come into effect very soon when we start solving exam related questions. Acceleration is velocity over time. These are very simple and true. So what we do, we say acceleration is given by velocity over time. So by taking now this L over T, we divide let me write from here. We divide by T, we have L over T squared. So this becomes the dimension for acceleration. This is also the dimension for acceleration. So now let's try to solve some examples. So this is our first example. It reads, show that the velocity, or show that V is equal to V naught plus A times T is dimensionally correct. Wow, what a very interesting question. So here we have been asked to show if this equation is dimensionally correct. Now, to know if the equation is dimensionally correct, the left hand side dimension should be equal to the right hand side dimensions. So the left hand and the right hand, the right hand is equal to left hand, or left hand then equal to the right hand side. Okay. So for us now to show if this equation is dimensionally correct, we need to know what are the dimensions of our left hand side, because to our left of the equation we only have V, and we know that the dimensions for V is L over T. We keep this equation and we go to the right hand side. We have V naught. V naught, this is just an initial velocity. I know most of us we are familiar with this equation. so I don't expect to have problem with this. Now let's compute, because v naught is just same as this v final, so the dimension for this and this are one and the same. So now let's try to compute a times t, acceleration times time. So this is our computation here. Acceleration, we know it is L over t times time, which is t. So when we multiply this, we will know that t will cancel with t, we will remain with 1t as the denominator and L as the numerator. Now when we look at this is equal to v naught also to v final. This is telling us v, the dimensions for v, the dimension for v naught, and the dimensions for acceleration times time are whole L over t. What is now our conclusion? After seeing that the left hand side and the right hand side are equal, we can conclude that the equation is dimensionally correct. Let's go to example 2. Check if this equation is correct. So our equation is x is equal to velocity times time squared, if it is correct. Now to start with, we are starting with the left hand side. Our left hand side x, we know that the dimensions for x is length, so the dimension for length is L. We keep this. The dimensions we start now for the right hand side, we know that the dimensions for v is this one, the dimensions for t is t. So when we square, because in the equation that we squared, we have t squared. Now when we multiply this and this, L over t times t squared, our result becomes this one. And from this, we can know that the right hand side is equal to this, and the left hand side is equal to this. We can conclude that the left hand side and the right hand side are not equal. That means the equation isn't correct.